making what I think is good progress, and I'd like to bring you a progress report. Problem is I have three things in my hand, so you can see how tridextrous I might be. The overarching framework, of course, is nuclear structure in general. What we're interested in is, in fact, nuclear matter. That's this little piece here of the action, but a whole lot of things follow from that little piece of action. We have a team, I call it my Honey Badger team at LSU. Honey Badger really goes after things in a real aggressive and hard way. And what we are really interested in doing is moving from fundamental principles through many-body theory to understand the collective features of real nuclei, something that folks here are quite familiar with. Stole this from Vitek Nesterowicz, who put it together a long time ago. But it does tell the story. You would like to start down in the high energy domain where you're dealing with the pork gluon soup, move through effective field theory to produce effective interactions, which should allow you to calculate from first principles the structure of atomic nuclei. That's the path. So once again, it's moving from fundamental principles to many-body theory. We use that. The no-core shell model has been a backbone of what we've done. We've got a symmetry-adapted no-core shell model that I'll introduce you to, and I'll introduce you to phenomenological approximation to that called the symplectic no-core shell model. Here's a picture of what the no-core shell model looks like. You're probably familiar to you. But the notion is that the shell model, take the harmonic oscillator basis, split up into disks, and at the 0 h-bar omega limit, you know you deal with just the valence shell, but of course now you allow for multi-particle excitations above the valence shell, going all the way up to what we call N max. Currently, for something like carbon, which we'll be looking at, N max, the maximum that you can accommodate with existing computational hardware is 10. Pushing it in the direction of 12, and we'll talk about that. But you do deal with realistic interactions. In principle, you get exact solutions. That means you diagonalize the Hamiltonian within the model space, and the objective is to reproduce binding energies and spectral features of light nuclei. Notice that it's a parameter-free theory, apart from the h-bar omega that you choose for the shell model, because you start with a realistic interaction. You do not append to it single particle energies or pairing or quadrupole. You take what you get from effective field theories. Basis states in this model are simply a Slater determinant of single particle configurations. The problem is there's a combinatorial growth in the model space with the number of single particle levels. And the higher you go, the larger it gets, and that's exponential growth, basically. This is a first view at what has been done with the no-core shell model. You see the various nuclei on the left and how high one can go in h-bar omega for those. But as I note, the range of applicability is limited by the combinatorial growth in the basis states. In contrast, what we're looking at is the same thing, but superimposed. Our basis will be symmetry adapted. In other words, we will have the symmetry available to us to look at and study, with the ultimate goal of being able to go to heavier nuclei, higher spaces, more highly deformed modes, cluster-like configurations, BE2s without effective charges, so on and so forth. And if I don't convince you that we're going there and that we've actually gotten there in some cases by the end of the talk, then I will have failed today. So that's my test for me. So there's the no-core shell model. Here's the symplectic, or the symmetry-adapted no-core shell model. It's the same space. If if you include everything. And for proof of principle, we do include everything, so we get exactly the same results in the test spaces that we've used. But the idea is, once you learn what's important about your model space, you limit it to that model space and yield parts of the space that aren't playing a significant role to those that are, which will allow you to climb the ladder in H bar omega to higher level spaces. By the way, a fact that's not often appreciated is that within this scheme, we handle spurious center of mass exactly. Even if you truncate, it's handled exactly, because the symplectic representations are complete with respect to the center of mass motion operator. So that's taken care of automatically. I think I'll skip this. This is the symplectic structure. For those interested in the algebraic things, it's the underpinning. The important thing is that what you're dealing with and what's included in the symmetry that you're dealing with is the quadrupole, the quadratic in the coordinates, the quadratic in the potential in the momentum, which means the potential energy is part of the kinetic energy is part of the model, and then you have the angular momentum and the mass and quadrupole calculation pieces. This is work that originated, of course, with Phil Elliott and Marcus Mashinsky in the 60s, thereabouts, 58. Elliott had started, and Mashinsky, it was continued to be non-compact version of that, with the thesis work of George Rosenstiel working with David Rowe. But I think that's all I want to say at this point. We can come back to it if we want. The important thing is that the algebra itself includes the giant resonances, and it includes the kinetic energy. And those are two very important parts that you have to keep in balance if you want to represent real interactions appropriately. I use this as a transition slide. There's a lot of people working in the like nuclei domain. Some of them are shown here. There's various models, including the one that I'm going to be talking about. But you've got to do a risk-benefit analysis, because if you're weak of heart, you wouldn't start this project. In fact, I think, Laurie Hurst, where are you? We've talked about doing this a long time ago, and didn't do it for two reasons. First of all, it's tough business. Secondly, the computational resources that you needed at the time weren't available. They are now. So here's the campaign that we launched ourselves on 10 years ago. The goal was to reproduce and predict properties of heavy as well as light, and we're focused on light now, nuclei, starting with and building upon QCD and effective field theory interactions that we get from that community. I call it QCD, EFT informed and inspired interactions. The plan was to exploit existing capabilities, to evaluate probable success of level and efforts to require the full balloon symmetry. We did this in the time frame of 2002 to 2006. We cheated. What we did is we had the no-core shell model results available. We analyzed the results of those calculations in terms of our basis and learned that most of what they were doing did in fact project at the 95% level down onto just a few key symmetries. So it's a good model. So we were anxious to move forward. And moving forward meant developing a shell model code that is symmetry adapted and has the same reach as the no-core. But you can look at the results and understand what's happening with the dynamics as you go. And that project was worked on with a thesis student and now postdoc, Thomas Dietrich at LSU.